I'm Professor Rad, and this is Precalc video 320, Composing Trig Functions, Trig of Trig Inverse. So in this video and the next, we're going to be talking about what happens when you try to compose trigonometric functions together. So in this video, we're looking at the outside function being a regular trig function, and then the inside function being the inverse trig function. So here's a note. If you have a trig function and you compose it with the inverse trig function of a value, they're going to undo each other perfectly so long as x is in the domain of the inverse trig function. In other words, if it's in the range of the original trig. So the way that I like to think about this one is I like to think about the range of the trig function because that's a little bit easier for me to remember. The other thing I want to point out is that with our trig notation, we have a tendency to drop parentheses because they kind of get in the way when we're writing stuff a lot. So when you see something like trig of trig inverse of x, really this is a composition of functions. So we have trig of something, and then we have inverse trig of something. So this is a composition of functions, so you can think of it as having those parentheses there. So for instance, in this first example, we have sine of inverse sine of 2/5. This is the standard way of writing sine of inverse sine of 2/5. So this is how the function notation we're comfortable writing. So if you feel like you might make some mistakes because the parentheses aren't there, feel free to write it with the parentheses, but otherwise you can feel free to write it this way here. Okay, now this is going to equal 2/5 so long as 2/5 is in the domain of inverse sine. In other words, 2/5 has to be in the range of sine. So sine has a range from -1 to +1, and 2/5 is in between -1 and +1. So this is going to equal 2/5. For this next one, we have tangent of inverse tangent of -5. So in order to figure out if this is going to equal -5, we need to think about the range of tangent. So the range of tangent is all real numbers. So if you have tangent and inverse tangent, they're going to undo each other to get -5. For this third example, we have cosine of inverse cosine of 3. So because our trig function here is cosine, we want to be thinking about the range of cosine. So cosine is going to go from -1 to +1, and 3 is not in that range. So this expression does not exist. And that's because you can't find inverse cosine of 3. Okay, it's a nonsense expression. Then for our last example, we have cosecant of inverse cosecant of 1/2. So again, we want to check is 1/2 in the range of cosecant. So cosecant, that's where we have like the u's on the top and on the bottom and that empty space in the middle. So cosecant does not exist between -1 and 1, and it exists everywhere else. So because 1/2 is between -1 and 1, it's not going to work. So this one also does not exist. So in summary, our trig function is going to perfectly undo the inverse trig function so long as the argument is where it needs to be. So if your argument is in the range of the trig function, it works perfectly. But we can compose not just sine with inverse sine, we could compose sine with, say, inverse cosine. So let's take a look at what that's going to look like. For this example, we're going to work through two problems, and we want to determine cosine of inverse sine of 8/11, and we're going to determine secant of inverse cosine of √3/6. So in order to complete these problems, remember that regular trig function, so like cosine, is going to take an angle as an input and spit out a real number as an output, a ratio as its output. So inverse trig functions work opposite. So inverse trig functions are going to take a real number as their input, and they spit out an angle as the output. So when you see something like inverse sine of 8/11, you don't want to think of that as like 3. You want to think of that as like some angle theta. So I find it helpful if I always equate inverse trig functions to angles, so to theta or alpha, as opposed to relating them to like an x, because x we're going to think of as a real number. So what we want to find is we want to find cosine of theta, where theta is given by this expression. So I'm going to write that out. For part A, we want to find cosine of theta where theta is inverse sine of 8/11. Now, when we have this notation that theta is the inverse sine of this function, what this is really telling us, think about like what we did with logarithmic expressions when we were finding, trying to write it as an exponential expression, right? Thinking of it in terms of its like opposite format. So here, if I have inverse sine of 8/11 is theta, that means that sine of theta is going to be 8/11. Or you could think of it as like taking sine of both sides, and sine inverse undo each other. So this expression means that sine of theta is equal to 8/11. So this problem, determining cosine of inverse sine of 8/11, boils down to problems we already know how to solve. They boil down to finding cosine where we know sine. Very cool. Now, the one other thing we have to bear in mind here, usually when we have problems of this type, we have information about where theta lives. So we do have information on where theta lives based off of our inverse trig and the restricted domains. So remember, some of our trig functions were restricted, not to the whole place, my goodness. Some were restricted just to the east, and some were restricted just to the north. So the trig functions that were restricted to the east, when we needed to find the inverse, were sine, tangent, and cosecant. And the ones that are restricted to the north are cosine, cotangent, and secant. So in this case, because we are undoing a sine function, we're looking at that angle. Sine was restricted to the east. So this means that theta is between negative pi halves and pi halves. All right, so now we have all the information that we need to complete one of those problems that we had looked at before. So I need to find cosine of theta. I know sine of theta, and I know where theta lives. So I'm going to use a Pythagorean identity here, and I'm going to say cos squared plus sine squared is 1. So we have cosine squared theta plus sine squared theta is 1. But sine is 8/11. So I'm just going to go ahead and square that as I write this in here. So that's going to be 64 over 121. So if I subtract that from both sides, that means I'm going to get, oh, I got to work this one out. Get 57 over 121. All right. So then to solve for cosine, we're going to square root both sides of that equation. And we're going to get that cosine of theta is plus or minus the square root of 57 over 11. Now 57 doesn't have any perfect square factors, so we can't simplify that radical any further. But I did square root 121 to get 11 back. So now we just have to figure out whether we want the positive or the negative radical. So theta lives between negative pi halves and pi halves. We're living in the east. So in the east, for cosine, the x value is positive. So because the x value is positive, we're going to get a positive answer here. So cosine of inverse cosine of inverse sine of 8/11 is going to equal positive square root of 57 over 11. All right, so why don't you take a moment and pause the video and try to do part B on your own so you can use this as your guide. Think about how you would take this expression and rewrite it as an old problem that we already know how to solve. Use the east and the north to guide you in determining where the angle is going to live, and see if you can come up with an answer. When you're all done, unpause the video and the answer will be on the board and we'll walk through it together. So let me get out of the way in case you need that, and you can pause the video here. Alrighty, so let's see how you did. So first I rephrased the question by saying, let's find secant of theta. So inverse cosine of root 3/6 is a theta. And this is going to mean that cosine of theta is root 3/6. Now cosine is living in the north. So we need theta to be between 0 and pi. So if I want to find secant and I know cosine, this is actually nicer than using a Pythagorean identity because secant and cosine are reciprocals. So the reciprocal of root 3/6 is 6 over root 3. And then we just have to, simplify that radical. So we'll get to multiply top and bottom by root 3 to get 6 root 3 over 3. And then that'll reduce to 2 root 3. So secant of inverse cosine of root 3/6 is equal to 2 root 3. So how did you do? Were you able to figure it out all right? Hope so. So let's make things a little more interesting and delve one layer deeper and look at an example of composing trig functions and applying, say, a sum or difference formula. Alrighty, so for this, our last example, we're going to find sine of inverse cosine of 3/5 minus inverse sine of 5/13. So don't let this heavy, inverse trig notation fool you, right? Remember that inverse cosine or inverse sine just refers to an angle. So I'm going to call inverse cosine of 3/5. Let's call that alpha. And let's call inverse sine of 5/13 beta. So this problem is really finding sine of alpha minus beta. So we're going to find sine of alpha minus beta where, now in this case, alpha is coming from this inverse cosine. So that means that we're going to have cosine of alpha equaling 3/5. And over here, we have beta is from this expression. So that means we're going to have sine of beta equaling 5/13. So we have sine of beta equals 5/13. Now, before I put a period on this and finish it, let's make sure we indicate the hemisphere, the north or the east, where alpha and where beta live. So for cosine, cosine lives in the north. So we need to make sure that alpha is between 0 and pi. And for beta, beta comes from sine, and sine lives in the east. So that means that beta has to be between negative pi halves and pi halves. All right, so that's our first step. And generally is the most helpful step, is taking the time to rewrite this inverse trig problem in terms of an older trig problem that we know how to solve. So stepping back, we've got sine of alpha minus beta, where we know cosine of alpha and we know sine of beta. So when we go to solve one of these problems, we need to know our difference formula. So remember, for sine, it's sine, cos, same. So we're going to need to know sine and cosine of alpha and beta for both. So let's jot down a little spot to write that summary. So let's say we have sine of alpha, sine of beta, cosine of alpha. And cosine's the one we know. And then we also need sine of beta, which is the one we know, and cosine of beta, which is the one we don't know yet. All right, so how about we break this problem down into chunks? So we need to figure out sine of alpha and cosine of beta before we can apply the difference formula. So pause the video here. You can use your trig definitions, or you can use the Pythagorean identities, to find either sine of alpha or cosine of beta. So pause the video here and work through that. And when you're done, we can check our answers together. Alrighty, so let's see how we did in finding sine of alpha and cosine of beta. So to find sine of alpha, I did cos squared plus sine squared is 1. Since cosine of alpha was 3/5, when I square it, I get 9/25. And solving that equation got me either positive or negative 4/5. I didn't mean circle the 4, I meant circle the plus, but that's okay. We'll just go with it. So for plus or minus 4/5, to determine out whether I need the positive or the negative, I go back here. Since we had cosine lives in the north. So that means I'm going to end up with a positive sign, because sine is positive in both these hemispheres or quadrants. So we ended up with a positive 4/5. For cosine of beta, I got 12/13 using the same technique. So I used the Pythagorean identity, I squared sine, and I solved for cosine. So because we had sine, that meant theta, or beta rather, lived in the east here. And in the east, cosine is positive in those two quadrants. So we ended up with a positive 12/13. So hopefully you were able to find alpha and beta okay. Or sorry, you were able to find sine of alpha and cosine of beta okay. Now we're going to apply this information with a difference formula to find what we need, sine of alpha minus beta. So I'm going to make some space for us here. And remember that sine of a difference, alpha minus beta, can be found using sine, cos, same. So we have sine, cos. Now I switch the angles, so sine, cos, and then the same operation, so subtraction. So now we just fill in and plug and jog. So sine of alpha is 4/5. Cosine of beta is 12/13. Sine of beta was 5/13. And then cosine of alpha was 3/5. Now, when I multiply these together, I'm going to avoid the temptation to simplify as I multiply, because I'm going to need to subtract these two. So for instance, even though these two 5s can cancel, I don't want them to, because I need the denominator here to be the same as the denominator here. So I'm going to leave it unsimplified till the very end. So for this first fraction, 4 times 12 is 48. And 5 times 13 is 65. 5 times 3 is 15. And 13 times 5 is still 65. So we can subtract these now. 48 minus 15 is going to give me 33. And I keep the 65. Now, in this case, this isn't going to simplify further because 33 is going to factor into 3 and 11, and 65 will factor into 5 and 13. So there are no common factors beyond 1. So that means this is going to be our answer. So sine of inverse cosine of 3/5 minus sine inverse sine of 5/13 is going to give us 33 over 65. All right, so that's going to conclude this video on trig of inverse trig. In the next video, we're going to work on composing the opposite direction. So we're going to look at the inverse trig of a trig function. A few other different things to keep in mind because of the restricted domain with our angles. So that's what we'll be looking at in our next video. I hope you found this video helpful in composing trig functions in this manner, and I hope you have a wonderful day. Bye for now.